Okay, welcome back, everybody. I'm really excited today because one of the big concepts of analysis is we're going to discuss today, and that's the concept of compactness. Now, compactness is a concept that when I first learned about it, it just seemed to me rather unmotivated and perhaps not. It wasn't clear for actually many weeks why we even cared about this concept. So I hope to teach you differently and maybe give you some sense of why this concept is important before we actually make the definition. So what have we been doing so far in this course? Well, we've been doing a lot of things, but I would say one of the big themes running through the material we've covered so far is this idea that when we're dealing with the analysis of the real numbers, we are wrestling with the infinite. Okay? We are, yes, music please. We are wrestling with the infinite. In what way are we wrestling with the infinite? You want to give me some examples from our last few weeks here? What way? Yes, Katie.
We have sets of numbers of which there are infinite numbers of numbers.
Okay, so for instance, the real numbers form an infinite set. Yes, and that was a little bit problematic at first because we had this idea that, once we started with, even the integers are infinite, right? But once we started defining other concepts such as fractions, we had to deal with the infinite pairs of numerators and denominators, right? And then we had this idea that there are gaps still, right? And we wanted to fill them in somehow, right? That's really wrestling with the infinite. Okay, what are some other ways in which we wrestle with the infinite? Well, we had this idea that somehow there are bigger sets, that the real numbers are somehow larger than the rationals, right? So countable and uncountable infinite sets. Later on, we're going to start talking about functions, okay? Functions, in particular, you think about functions in calculus, you graph them, right? You're usually dealing with things like continuous functions. Well, what does it mean for a function to be continuous? That's really wrestling with the infinite, right? Because if I had a function on a finite set, that'd be rather boring, right? You don't have to talk about the relationship between a value of a function at this point and the value of a function at this point, right? A function on a 3-point set is just a three-dimensional vector, isn't it? Right? You put a number here, you put a number here, you put a number here. Okay, rather uninteresting from the point of view of analysis. We're going to start filling in the gaps later with continuous functions. Okay, so we are wrestling with the infinite in this course. And the other, of course, theme that I want to hammer home, if it hasn't already begun to show itself, is that finite sets are nice. Okay, why are finite sets nice? Well, they're small. That's one thing. Okay, there's only finitely many things. They're small. Can't say it any better way than that. Okay, of course, the associated concept here is boundedness, which we will talk about. What's another reason finite sets are nice? Well, they're closed sets. In fact, they're trivially closed. A closed set is a set that contains all its limit points, and finite sets have no limit points. Okay, so they clearly contain their limit points. This will become apparent why we care about this soon. In the metric space that's the real numbers, the finite sets actually contain their supremum, right? That's one of the things you showed on your homework exercise from a couple weeks ago. And if they contain their supremum, then we can rightfully talk about a maximum or a minimum, right? You give me a set of finite numbers, I can say there's a maximum and a minimum. What I mean is there is a supremum and it's in the set. Yes? With me? Okay, and one other reason we care about finite sets is that whenever you do anything with finite sets, the process terminates. Okay, so if I say I'm going to do something on a finite set, I know that there will be an end, that this process will end. Okay, so these are all great reasons why we care about finite sets and why they're nice. but we're wrestling with the infinite in this course. Okay, so the concept of compactness is really about finiteness. In particular, if you have a set that is compact, this is the way I like to think about it, it is the next best thing to being finite. Okay? It's the next best thing. Now, when I make this definition, it's not going to be apparent why any of these things are true about compact sets, but they are. Okay? So each of the things I've just mentioned about finite sets are also things that are true about compact sets. As the name suggests, compact sets are compact, right? Which is sort of a way of saying that they're small in some sense. Okay. Okay, very good. So let's make some definitions. Let me erase some of the scratch work here that remains. Make some definitions, and then we'll see why this is a important concept. So the first thing we have to do is we have to talk about what it means to cover a set. So here's the definition. So what do you think? I'm going to make a definition of an open cover of a set. And as the name suggests, what do you think I might mean by the words open cover? Open cover of a set. Okay, that might be a little more complicated definition than we want. So an open cover is just going to be a collection of open sets that cover a particular set. Okay, so here is let's call this set E. This is living in some X. Okay, X is always a metric space from now on. An open cover of some set, whatever it is, E, in X is a collection of sets, of open sets, if it's an open cover. It is a collection of open sets, which I'll denote, let's say, G sub alpha, whose union covers, if you don't like the term covers, a more mathematical term would be contains E. Okay, and this is all living in some metric space X. Okay, so maybe I should put this in your notes so that it gets there. I'm just going to say from now on, X is always a metric space. Whenever I use the letter X, I imagine it's endowed with some metric. Okay, so a picture might be something like the following. Let me grab my colored chalk here. So here is some set E, and I have a bunch of open sets, which, okay, usually you dot open sets, dot the boundaries, but that's hard to draw a lot of. And so the way, another way to sort of notate an open set is kind of draw it curly, okay? So you just imagine these are the open sets whose union contains all of E. So is this a cover of E? No, I've missed some points. Yes? So maybe I'll throw in one. There is an open cover. Okay. Okay, so any questions about the definition of an open cover? I should mention that sometimes we just say the word cover because we're never going to talk about any other kind of cover. Okay? Okay. And while we're at it, let me actually put another definition here. And that is the concept of a subcover. What do you think a subcover is? Take a wild guess. What is a subcover? Yes. Excellent. So it's a subcollection of G alpha that is still a cover. So good. So a subcover of G alpha is a subcollection. Notice that when I talk about a subcover, I'm always talking about with reference to some open cover. Okay? It's a subcollection, and here's how we denote a subcollection. If the subcover is G alpha, and alpha is from some index set, this could be possibly uncountable. The subcover would look something like G sub alpha, and I want to denote that I'm picking specific alpha. Okay? So I might do the following. I might look at specific alpha and label them. This is going to appear funny, but I might label them but with its own subscript, gamma. Okay? Usually later on, gamma will just be a finite set. Okay? But this is one way to write it. Is a subcollection that is still covers E. Okay, question. If I take a cover and I take the subcollection that's all the sets, is that a subcover? Yes, it's still a subcover because it still covers. I haven't removed any sets. In this picture, maybe E looks like, maybe E looks, let me throw another set in here. Would you agree that this set I just threw in is kind of extraneous? So all the green sets form a cover, but I don't need all of them. I could throw this one away. The rest would be a subcover. Happy? Okay. Okay, good. So two important concepts here. Let's look at some examples, specific examples. How about an example in the real numbers? Let's look at the set. How about 1/2? Include 1/2, but don't include 1. So it's the half open interval. And I claim the following as a cover. See if you agree. So I claim this has a particular cover, which I'm going to call V sub n, where Vn is a interval, an open interval, 1 over n to 1 over 1 minus n. Okay, so picture please. 1/2. 1. And what are the sets here? Well, I probably should start, so this isn't empty, I probably should start n at what? How about 3? Okay, so by subscripting it with an n, this is a collection that's indexed by the natural numbers, and I'm starting at 3, and this just means keep going. Okay. Okay, so what does this set look like? Or what does this cover look like? Each set looks like, the first set is 1/3 to 2/3, so it might look something like this. There's the first set. Yes? What's the second set? 1/4 to 2/4. 3/4. 1/5 to, I actually have to do math. 4/5. 1/6 to 5/6, etc. And you can keep going. You get ever increasing intervals. Yes? Are these open sets? Is this an open cover of the set that goes from 1/2 to 1, not including 1? Yes. Why? Well, we're not going to, we'll just say why. Is it clear that 1/2 is covered? Yes, by all the sets. Is it clear that 3/4 is covered? Yes, not by V4, but by V5. Yes? And would you agree that any point just to the left of 1 eventually gets covered by one of the sets? Yes? Okay. Good. So this is a cover. But there are lots of covers for this set, right? It also has the following cover. How about the cover that just goes from 0 to 2? Just one set. So this cover has one set. Is this an open cover? It consists of one set like this. Okay. Yes? Happy? Yes. So the curly braces indicate a set. And the parentheses indicate the bounds of this interval. So this is the set containing one element. This is a set containing many elements where I've indexed them by a natural number. Okay? Excellent question. If I left this off, this would be a single set, but I'm talking about a collection. So just to be really precise, I'm saying this is a set containing one element. Okay? Yes? Ooh, excellent question. So the question is, do we ever need an uncountable index set? And the answer is yes for some metric spaces, although it turns out for most of the metric spaces that we care about, you could have a countable collection, but sub-collection, right? But for instance, here's a cover of the real numbers. Let's take all balls centered at any possible point. That's an uncountable collection of open sets. Okay. So yeah, in fact, let's do this example here. Oh, so it has another cover. Also, it has this cover. How about the cover? Let's call this W sub x, where W sub x is, and this is all x in 1/2 1. So this is kind of a cute trick. I have a cover here where for every point in this set, I have an open ball around that point. How about an open ball around x of radius 1/2? Would you agree this is a cover of the same set, and basically around every point I'm taking a ball of a particular radius? 1/2 is huge, actually, right? So this is much, the picture is bigger. But okay, to make this just a little more interesting, let's make this 1/10. How's that? Then that's more like this picture. Would you agree that this cover just consists of a bunch of balls around points? And how many of them are there? Uncountably many, one for every point between 1/2 and 1. Are you with me? These are all covers, yes? So one of the questions that you want to ask is, do we need everything in the cover? For these particular, I gave you 3 different covers of the same set. Do we need all these sets? Given a cover, so here's a big question. Given a cover, do we need all these sets to still cover the set? Okay. So let's look at these 3 covers. The V's. Do we need all the sets to still cover this set? Yes? Well, I claim I could throw out the first one and it'd still be covered by the others. Yeah? Okay. So the answer to the first one is, well, no, I can throw some away. So notice that in the first example, 1 half, so Vn, which goes from 3 to infinity, has a subcover. It has lots of different subcovers, but here's one. How about Vn that goes from 122 onward? Would you agree this still covers the set? Would you agree I could throw away the first few intervals and still cover the set? Yes? Okay. What's that? The first very, very many. How about the first million? I could throw them away, and the rest still cover. Yes? Okay, good. Let's see. What about this cover? Does it do? I can't throw away it. I can't throw away the one that's there. That's right. So this actually has a subcover, but the only subcover is the one that the original cover. Okay. What about this one that contains uncountably many? Can I throw away some of these sets? Willie's nodding. Yes. How many can you throw away? Do you want to throw a lot? Throw a lot away. Give me a cover that. So Wx has a subcover consisting of. Okay, you could choose just the rational points. That would certainly be a subcover. There's even a smaller one. I could think of a smaller one. How about one that's centered at, let's say, it's centered at the point a half, and well, here, let's make it easier on ourselves. 5/10. If it's centered at 6/10, these are radius a tenth, right? So they'll overlap. 7/10, 8/10, and I think that's enough. No? 9/10. Would you agree this is a subcover? Not only is it a subcover, there's only finitely many of them. So it is a finite subcover. Are you with me? This is the picture. Looks something like this. They're just a few sets here. Like so. One. They just overlap like this. And I think that covers everything from 1 to a half. Everybody with me here? Okay, so why do we care so much about open covers? Well, that will become apparent shortly. Let's see here. Let's do one more example. How about the following? Suppose I took this set. How about 0, 1? In R. By in R, I'm telling you what metric space I'm in, so you know what set to pick the open sets from. Okay, so would you agree it has a cover by the same sets here, Vn, except Vn doesn't cover what? Or 0. So I should throw in a few things extra. So by the Vn and union, so I'm going to throw in by the Vn union a set containing, I'll call this W0 and W1. Oh, actually, that's good. I like it. It's actually used the same notation here. Okay. So it'll be W0 and W1 basically cover the endpoints. 0, 1. So these special sets, purple sets, W0 just goes from -1/10 to 1/10, and 1. So this is W0 and W1. And all the other sets look like before. Would you agree this is a cover of this interval? Everybody say yes. Okay. Do I need them all? Does it have a subcover that's proper, that doesn't use them all? Which ones can I throw away? I can throw, so does this suffer from the same problem as this? That is, does this set have it has a subcover. Does it have a finite subcover? This one up here? No, because no matter how far you go, you won't, with only finitely many sets, you will not cover everything, right? If you had, let's say, finitely many sets, then there's a largest index. The largest index might be 22 million. Would you agree that that one set, the V sub 22 million, wouldn't cover everything? It covers all the other sets, so you can throw the other ones away, but it won't cover the endpoint. So this creature does not have a finite subcover, this cover. Whereas for this set, this cover does. It has a cover by this, and it has a finite subcover. A finite subcover is, in particular, can you name one? How about W0, W1, and V11 would do? Happy? Okay, great. We are ready now to make our definition for compact. So when I put up this definition, you should ask yourself, why is this somehow saying the set is small? Okay. So here's a definition. We're going to say that a set K is compact. Usually, of course, you're referring to some metric space. But as we'll see later, you don't actually have to refer to the metric space you're embedded in. But I'll put it here for now in parentheses. If every open cover of K contains a finite subcover. Okay, this is the huge definition, so I'll box it. A set is compact if every open cover of K contains a finite subcover. All right, so what is this saying? It's saying that to show that a set is compact, you want to show that every open cover has a smaller subcover that's in fact finite. Okay? Or to say another way, if you want to show a set as not compact, that means there is what? There is a single open cover that has no finite subcover. Okay, so I'll just say so K is not compact means there exists some open cover with no finite subcover. Okay. We can wrap our brains around this definition. Let's look at some of the examples. I claim in some of these examples we've already perhaps seen that some of these things are not compact. Why? Well, to show something's not compact is actually pretty easy, right? You just have to find a single open cover that has no finite subcover. Yes? So, is 1/2 1 compact? No. What do you mean no? There's a cover that's finite. But that's not the definition. Okay, so this is a huge caution. A lot of times when people learn this definition, they think that the definition is saying that a set is compact if there is a finite cover. That's not what this definition is saying. Okay, so let me just say, warning. We are not saying this definition is not saying there's a finite cover. That's not what we're saying. Clearly not what we're saying, because every set has a finite cover. Just take the whole metric space. Isn't that an open set? Yes? That will cover everything. So this is what we're not saying. Not saying this. Okay, good. 1/2 1 is not compact because there is an open cover with no finite subcover. Which one? The VNs. Okay, so example 1/2 1 is not compact. And I'm going to abbreviate compact by CPT. And this is witnessed by the fact that the VNs, see the VNs. Maybe that's just what I'll say. Happy? What else do we know is not compact? Let's do another example. How about Z? I claim Z in R. The subset of the consisting of the integers I claim is not compact. Can you see why? Let's see. Here's the set, Z. Yes? I claim it's not compact, which means show me a open cover. Don't start with subcover, please. Don't. Okay. Show me a open cover that has a, or that does not have a finite subcover. Can you think of an open cover of Z by open sets, open intervals, that clearly has no finite subcover? 1 to n? Yeah, so you might even, you're taking concentric open balls. I'll do something that may be even more obvious that you can't find a finite subcover. How about covering every integer point by a little interval around it? Can you argue why this has no finite subcover? Good. If you take any one away, you can't even remove one without destroying its covering property, right? Because you take this one away, that integer won't be covered. With me? Okay. So Z in R is not compact. What about the closed interval 0, 1? Well, let's see. This particular open set, this particular cover, open cover, has a, does it have a finite subcover? Yes. Okay. Does that mean it's compact? Not necessarily, because I need to show that every open cover has a finite subcover. So 0, 1 may be compact. We don't know that yet. Although secretly, of course, I do. I know the answer. Okay, but I want to let you, if you don't know the answer, puzzle over whether this is true. 0, 1 may be compact, but I need to check every open cover. Oh my gosh, there could be a lot of those, right? Or prove a theorem. Okay, so that's what we're going to do later. Okay. All right. Let's see. What else? By the way, notice with 1/2 1, it's not compact because there is an open cover with no finite subcover. But that doesn't mean that there couldn't be some open covers with a finite subcover, like the W's. With me? So this is just to show something's not compact. It's generally a lot easier. You just have to exhibit an open cover with no finite subcover. Okay, so here's a question. We said something about open sets. We said something about compact sets being somehow the next best thing to being finite. Yeah? Okay, so it sure would be nice if finite sets were compact. Are finite sets compact? Yes? So, theorem. Finite sets are in fact compact. Let's see, you can give me an argument. I know you can. This is actually an example where you can show every open cover has a finite subcover. Proof. Let's suppose you have an open cover. Consider, a way of saying look at, some open cover. This is an arbitrary open cover, so G sub alpha. So let's see, I'm going to draw a picture here. It's probably easiest. Here's a picture. And here are some open sets that cover this finite set. How about this one? How about this? How about this? How about this? How about this? And maybe there's like, concentric circles here, and there's lots of them, maybe infinitely many. And maybe there's lots that cover a particular point. Can somebody give me an argument why a compact set, why a finite set, this open cover has a finite subcover? Can you think of finite subcover? Yes. Excellent. Yeah, so every point could be in lots of sets, but just pick one. And when you pick one, you can pick one for this, pick one for this, pick one for this, pick one for this, and pick one for this. Would you agree it's now covered? So that is a finite subcover. So how would we write that? Let's be careful. So consider open cover G alpha. Let's say it covering our finite set, x1 through x sub n. So what should I say? I think what we want to say, take one for each of these. Take one G sub alpha. So for all x sub I, choose, I don't care which one, just choose one, G sub alpha. And now, of course, to show that this is a specific alpha, I'm going to say G sub alpha sub I. So this is, I'm taking a subscript to say I'm picking something for the original collection. Choose one G sub alpha sub I from the collection that covers, that contains x sub I. And this is the same index. And now the claim is, then, okay, now you'll see that the advantage of this notation now. Then I can refer to the G sub alpha sub I, the ith index, and now the i's just go from 1 to big N. Covers the set. Done. Okay? Everybody happy with that? Pretty nice, right? Finite sets are, in fact, compact. Ah, okay. Very, very good. What else is compact? Well, we're going to have to prove some theorems to figure out what else is compact. Let's see what we can say about compact sets. If we can prove some things, might give us some intuition for what compact sets look like. We really have no intuition yet. So here's a theorem. I claim compact sets are bounded. Okay, so I have to define bounded. So remember, we're in some metric space. Let me just make a definition. Definition, a set K is bounded. I'm going to abbreviate bounded by BDD. A set K is bounded if, suggest a definition for me, for an arbitrary metric space. What do you think it means to be bounded? Emil? If there's some ball that contains the entire set? Yeah, that's a good definition. If there's some ball that contains the entire set. I like that. It's different from the one in the book, but it's equivalent, right? So the one in the book says a set is bounded if there is a, well, actually, it is equivalent. It's exactly what the book says, but you've just said it in a lot nicer way. If there's a point and a radius such that the ball around that point contains everything. So I'll just say that. That's good. If K is in, I'll say it this way, n sub r of x for some x in big X. Okay, so if it's in a big enough ball, then the set is bounded. Picture. Here's a set K. Now the ball doesn't have to be centered around any particular point in K. It could be in just an X. This is a bounded set because it's in a big enough ball. Okay. Now let's show, in fact, that compact sets can't be too big. They're small. They're bounded. Okay. And let's see. I claim in this proof, a very nice proof, you will see why this is somehow related to being finite, the next best thing to being finite. Help me. Why is it the case that a compact set is bounded? Well, what do I have? What's the hypothesis now? Let's give the set a name. So here's a proof. Suppose K is compact. Let K be compact. That's a good place to start. I want to show K is bounded. Help me. If it's compact, that means that everybody say this together, every has a finite subcover. Good. So if you have a set that's compact, it means that you can pick any cover you want and use the fact that I know that that has a finite subcover, yes? So let's pick a good open cover. That will help us show that this set is bounded. Raise your hand if you have an idea, and I'm going to just see how long, wait until enough people have an idea to show this thing is bounded. If the compact set is, how can you show this set is bounded? How can you show the set is bounded? Rebecca? Okay, so we want an open cover that contains K. Which one? Oh, okay. If it has one set in it, I guess it's, what set would that be? Now, of course, how do you know there is a neighborhood that contains K? You want it to, but now what you would have shown is that any set, if your proof were true, that would show that any set is bounded, which is definitely not true, right? And the problem, of course, is the one set that might contain K might be the entire metric space, right? It's not necessarily a neighborhood. So can you think of some open balls that cover this that might be helpful? What do I want to do to show that this set is bounded? I really want to do what? I want to show that, in some sense, the distance from this point to some other point can't be too big, yes? So it might be helpful to cover the set with a bunch of balls of what radius? I don't know, pick one. What if I had balls of radius 1? So let's start with now another picture. If I had a bunch of balls of radius 1, that's a lot of them, isn't it? I could use that trick over there. Do you see the W sub x's? Okay, I'm not going to draw them all. But you can't stop me from dropping them all. Okay, but I'm not going to. Okay, there's a lot of open balls here, yes? Radius 1. What's compactness going to give you? A cover by finitely many. Now, why would that help you show this thing is bounded if there are just finitely many balls of radius 1? Suppose there were 17 balls of radius 1 now that covered this thing. Or how about just a bigger one? A ball of radius 17 you claim will now cover everything, or something like that. Actually, it would be 17 plus 1, perhaps, right? So do you see how finiteness is now playing a big role here? Because this cover has a finite number of balls that form a subcover, nothing can be more than 17 balls away. And these are all radius 1. Yes? Okay, let's write that down. This is very nice proof. Let K be compact. And then notice that let's say the set W of the ball, I'm going to call B sub 1. No, I'll just call this N sub 1. No, let's just, so we'll make our lives a little easier. We'll write, let's let B sub X be N sub 1 of X. This is the ball of radius 1. So now the first thing to note is that you have an open cover. So the one open cover might be, let's take the ball B sub X such that X is in K. Would you agree that's exactly like this example here? This is just a ball around every single point of particular radius. Yes? Happy with that, Drew? Happy? Okay. Okay. And now Sarah's thinking, oh, this is an open cover. Of what? Help me? Okay. By compactness of K, there exists a what? There exists a finite subcover. Now, how would I denote the finite subcover? Remember, this is indexed by X. So Steve is thinking I should just do what with the X's? If I want to indicate somehow they're finitely many. How about indexing the X's by numbers? So let's do this. There's a finite subcover B of X sub I, where I goes from 1 to some number n. Happy with that? Yes? Okay, we're almost there. Ran out of space on this board. What should I say now? Help me make precise this idea. If there were 17 sets now that covered this whole thing, what's the bound? And what's the center of the ball that you're going to use? Well, how about any point? How about x1? You know, this is x1 through x17. How about x1? How far apart will the other points be from one of the centers if there were 17 balls? Well, at most 17, or if you like, if you just want to say it another way, is pretty easier. An easier way might be, would you agree the set of all pairwise distances is finite? Willie? Excellent question. Yeah, so what if the set is disconnected and you had 17 balls? So this is still part of K as well. So that's one of the problems with this crude picture is that if there were 17, you might not have any relationship between these two, right? And so that's why I'm going to recommend another strategy. Because if you tried to write this proof down, you would fail, right? Because of exactly this issue. So another way to do this is to look at all possible pairwise distances. How many such distances are there? finitely many. Therefore, I can take the maximum. That number is achieved because it's a finite set. That maximum is a maximum distance between centers. So then how much farther can any other 2 points be? 2 more, if you happen to be right at the very edge. Here's one center, here's another center. The points that are farthest from these balls is this distance plus 2. Yes? And that, would you agree, Willie, solves the disconnected picture? Beautiful objection. And we've taken care of that. So here's what we're going to do. Let's let big R be the maximum of the pairwise distances dxi, dxj, where xi are I and j are between 1 and n. And now you should tell the reader that this maximum exists because what? Because what? Set is finite. The set x1 through xn is finite. Okay? Happy with that? Okay, so then here's the ball. We claim some big ball around x1 of radius. How about big R plus 2? That would do, wouldn't it? Contains all of k. Now, there's something to show here, but I'm not going to do it, but you can see what to do, right? If you want to show this contains all k, you would use what? What property of metrics is going to become really important in here? Triangle inequality, because you're just bootstrapping from one point to, every point is in some ball, xj. Distance from x1 to xj is bounded by r, and the other distances are bounded by 2. Actually, in this proof, I didn't even need xi, xj, did I? I could have replaced this by what? x1, xj, and take that maximum. Okay. All right. Everybody happy? What have we just done? We've defined compactness in a very curious way. We have shown that compact sets are somewhat like finite sets. Finite sets are, in fact, compact. Compact sets behave in the same way finite sets do, namely that they're bounded. Okay? And so I want to take a couple-minute break, and after the break, I want to show you that the concept of compactness is an intrinsic notion of the set, and it doesn't matter what metric space you're in. Okay? So let's take a couple-minute break. Okay. Let's resume. So we have this property of a set that we call compactness. And of course, we've learned lots of other properties of sets, right? A set could be open, a set could be closed, one set could be dense in another set, etc. These are all notions of definitions that we've learned for sets in Rn. What I want to show you is that the notion of compactness is actually an intrinsic property to the set. It doesn't matter what metric space you're in. That's different from some of the other notions. So, for instance, if you think about an open set, would you agree this set is open in R? Yes? Yes? But if I view this set as being embedded in R2, this set is no longer open, is it? Not every point is an interior point. Certainly, and what's wrong? In R, a neighborhood looks like this, doesn't it? But in R2, what does the neighborhood look like? It looks like a whole disk, doesn't it? And so this particular set, as a subset of R2, is no longer open. Are you with me? Okay. So it's not open. in R2. As, what do I mean? Well, I'm viewing this now as a subset of A, B, where it's the y-coordinate 0, A0, where A is in 0, 1. So viewed as a subset of R2, it's no longer open. So openness actually depends on what set you're in. Yes? What I want to show you is that compactness does not. Okay? But before I do that, I have to explain to you now how we relate the notions of openness in one set when it's embedded in a bigger set. Okay? So I began with an example, but this is all part of the question of what it means to be open, open relative to a particular metric space. So let me title this portion Relative Open Sets. So let's be very careful about what we mean by open. We defined what it means for a set to be open before, but now let's think a bit about the metric space that we're in. So suppose you have, first of all, would you agree that if I had a subset of a metric space, Y, and this lives in some X, would you agree that Y is also a metric space? Why? X has a notion of distance, a metric, yes? And therefore, you can apply the same metric to the points in Y, because it's just a subset of X. Are you with me? Yes? Ah, okay. So we say that Y inherits a metric from X. Okay, this is Y inherits a metric from X. So Y is in X, that's metric. Then Y is a metric space. And then Y inherits a metric from X. Okay, so picture in your head is something like this. Here's a metric space X. Here's a smaller set, Y. Okay. And it's also a metric. Okay, so if we're going to define what we mean for a set to be open in Y or in X, we need to come back to the definition. A set is open if every point is a interior point. Oh, but what does it mean to be interior? A point is interior if it has an open ball around it. It's contained in that metric space, yes? Clearly, it's what you meant, but now we have to worry about which metric space we're talking about. Okay? So let's talk about what it means to be an open ball. Can you see a situation in this picture where the notion of open ball in Y and open ball in X might be different? Yeah. How about a point over here and a ball around it might look something like this. In X, here's an open ball. An open ball should be the same radius, but okay. You get the picture, yes? Now what's an open ball in Y going to look like? I mean, this is distance R, isn't it? Some radius R, that's an open ball. What is that open ball in Y going to look like? This is an open ball in X of radius R around the point X. So maybe I'll just notate that here. That's N sub R of X in big X. What about if I'm just talking about the space Y? What is the open ball going to look like? It's going to be smaller? Smaller radius? No. Same radius, but what? It's going to be just the stuff on inside of Y. Yes? So that is N sub R of X in Y. Everybody see the difference between the two pictures? Okay, good. So now the question remains, what's the connection between sets, general sets that are open, not just open balls, General sets that are open in Y versus general sets that are open in X. So same picture. Here's, oops, X. Here's Y. Okay. And now suppose I have some, so I want to know, when is a set in Y going to be open? Like, can I give a criterion that would help me decide when a set is open? So here's an example. Suppose I take this set. Is this set of all stuff on this side, is this open? And I'm gonna include this boundary here because that's also in Y. So how many people say this set is open in Y? How many people say it's not open in Y? Okay. Why not? What's it mean to be open in Y? Well, it means every point is a what? Interior point. Is this point an interior point? Yes, because it has a ball around it, like that one, in fact. In Y, that's still open. So would you agree this point has this ball inside it? This is the open ball around X that's in Y. Yes? Okay, well, that point has is an interior point. Some of you said you don't believe this set is open in Y. If so, you have to show me a point that's not interior. What's a point that's not interior? Any point on where? On the edge? You don't think this is interior? It has a ball around it in Y. That's contained around the point. How many people think this set that I've drawn is open in Y? Okay, more of you now. Do you agree? It has neighborhoods. It's just that you forget everything outside, and it's still, this is definitely all the points in Y that are distance R from this point X. Yes? With me? Okay, very good. So, this set is open in Y. Is it open in X? No. But is there a relationship between sets that are open in Y and sets that are open in X? I claim there is. A very nice criterion. And the criterion is a set is open in Y if there, it turns out, if and only if there exists a set in X that is open, whose intersection with Y is this given set. Okay, so let me call this set a name. We'll call it E. And here's the theorem. Let me just make the definition so that we have this here. So a set is open. A set U is open in Y. And the book says open relative to Y. You often hear that. If, this is what it means. So this is a definition. It's a definition if, right? It's not a conditional if. If every point of U is an interior point of U. And of course, the key difference here is that the notion of interior means using neighborhoods in Y. With me? Okay, using those kind of the funny possibly half cut off disks, right? Okay, so this is no different than the definition you had before. We're just paying attention to what set we're living in. So openness matters. The metric space matters for the concept of openness. So here's a theorem. E in Y in X, suppose E is a subset of Y and Y is a subset of X, like that picture. Then the claim is E is open in Y if and only if E is y intersect G for some G open in X. That's a very nice criterion because it allows us to pass between sets, open sets in one space and open sets in a bigger space. First of all, do you agree? Does this seem believable? It's an if and only if. I claim one direction. So here's a proof idea. One direction it should be fairly obvious. Would you agree that if you have a set G, then its intersection with Y has got to be open in Y? Why? What does that mean to be open in G? Well, it means that every point has a neighborhood around it in X that's also in G, yes? So in Y, what's the neighborhood you're going to use? The same one, but just restricted to Y. Yes, Lindsay. So to say something interior point, you're referring to a particular set. So the claim is that if X is interior to G, then it's interior to E using possibly cut off neighborhoods. Does everybody believe that? That's basically using this correspondence between neighborhoods in X and neighborhoods in Y. So the proof idea in the backwards direction uses the fact that if n sub r of X is in G, so take a neighborhood around X in G, then n sub r sub X in Y is the neighborhood. Oh, maybe I should say intersect Y is a neighborhood of X in Y. So if this witnessed the fact that it was interior, this one would witness the fact that it was interior to Y, to E and Y. It's a neighborhood of X in Y and in G, and in E. Happy? That's that direction. What about the forward direction? Help me. If a set is open, look at the red set here. That means that around every point there's a neighborhood, but possibly a cutoff neighborhood that's in E. Can you think of a set big G that would also then be open? Suppose you have a bunch of cutoff neighborhoods. What could you do to those neighborhoods? Include the stuff that it suggests, yes? And then what will the set G be? Well, what is it? Define G. Yes, union all these neighborhoods. So if I missed this part, include it. So then why is the union of a bunch of open balls open? Well, by definition, because every point now has a neighborhood, it shows that it's interior. Okay, great. So in this case, if E is open in Y, E open in Y means every point X has a neighborhood, n sub r of X, that's completely in Y and in E. But then the same neighborhood in X can be used, and I'll take the union of all these for all the points. Which points? Oh, so this R depends on X, n sub R sub X. X for all X in E. Then this in X is an open set, is open. So we'll call it G. That completes our argument. Okay, any questions about this proof. Basically, the upshot is I can tell when a set is open in a smaller space just by seeing if it's the intersection of something from the bigger space. Okay, that's also open. Okay, so what we want to do next time is I want to show you then that if you say a set K is compact in X, it's equivalent to say a set K is compact in Y is equivalent to saying a set K is compact in X. So compactness really doesn't depend on the metric space that you're in. To say that a set is small really doesn't depend on the space that you're in. Okay? And then we want to show some other analogies with finite sets. So that's next time. Okay, stick around.